close your eyes and imagine just for a moment that you are floating, not falling, not rushing, simply drifting, weightless and still, somewhere far above the world you know. Below you, the earth turns slowly, wrapped in its thin blue veil of atmosphere. And above you stretches something so vast, so ancient, so quietly breathtaking, that no single lifetime has ever been enough to take it all in. This is space. And tonight, we're going to wander through it together. Let's begin at the beginning, or at least as close to the beginning as we can reach. The universe is approximately 13.8 billion years old. That number is almost impossible to hold in your mind, and that's perfectly all right. You don't need to understand it fully. You only need to feel the weight of it, this deep, slow, unimaginable stretch of time that existed long before our sun, long before our Earth, long before any eye had ever opened to look up at the stars. And yet, despite all that time, space is still mostly empty. Truly, profoundly empty. If you took all the matter in the observable universe, every star, every planet, every moon, every grain of cosmic dust, and spread it evenly through all of space, you would end up with, on average, less than 1 atom per cubic meter. Just one. A single lonely atom, in a space the size of a large cardboard box. The universe, at its heart, is a great and peaceful silence. But within that silence, there are islands of light. Our own island, the Milky Way, is a spiral galaxy, slowly turning like a pinwheel of stars. And it is home to somewhere between 100 and 400 billion stars. Not millions. Billions. Each one a sun in its own right, many of them larger and brighter than our own, some burning blue and fierce, others glowing red and ancient and slow. Our sun sits quietly about 2/3 of the way out from the center of this great spiral. Not at the heart of things, not at the edge, but tucked comfortably in between, in a calm and relatively quiet neighborhood. A good place, as it turns out, for life to take its time. Now, light travels faster than anything else in the universe. In a single second, a beam of light can travel nearly 300,000 kilometers. It could circle the entire Earth more than 7 times in the time it takes you to blink. And yet, even at that almost incomprehensible speed, light from the sun still takes about 8 minutes and 20 seconds to reach us here on Earth. 8 minutes. That's the distance between us and our star. So when you close your eyes tonight, the warmth you felt today on your face was light that left the sun before you'd even poured your morning coffee. And our sun, for all its warmth and size, is considered just an average star. Nothing exceptional. A yellow dwarf, astronomers call it, which is perhaps the most underestimated name in all of science, because to us it is everything. But in the grand catalogue of the cosmos, it is simply ordinary. There are stars out there so large that if you placed one where our sun sits, its surface would extend past the orbit of Jupiter. Stars so enormous that our entire solar system would fit inside them with room to spare. And yet they burn so bright and so hot that they exhaust themselves in just a few million years, cosmic mayflies, living fast and dying in spectacular, violent bursts of light. Our sun, by contrast, has been burning steadily for about 4.6 billion years, and has roughly another 5 billion years left to go. Slow, gentle, dependable, like a lantern in a long, long night. Speaking of that night, the darkness of space is not entirely dark. If you were to travel far enough from any star, far enough that the light of every sun in every galaxy had faded to almost nothing, you would still find yourself bathed in a faint, faint glow. A warmth left over from the very first moments of the universe itself. This is called the cosmic microwave background, the afterglow of the Big Bang, stretched thin across 13 billion years of expanding space. It is the oldest light in the universe, and it surrounds us still in every direction day and night, a whisper from the very beginning of everything. Settle in a little deeper now. Let your breathing slow. There's no rush here. Space has been waiting for you. It will wait as long as you need. We have 91 more facts to explore, and all the time in the universe to find them. One of the things that makes space so easy to get lost in is the sheer generosity of it all. Wherever you look, truly wherever, there is something extraordinary waiting quietly to be noticed. Not loudly, not urgently, just there, patient and vast and indifferent to whether anyone ever looks at all. And perhaps that's part of what makes it so restful. Let's drift a little closer to home for a while. Let's stay within our own solar system, this small, familiar corner of the cosmos that we've called home for as long as home has existed. Our solar system stretches much further than most people imagine. We tend to think of it as ending somewhere around the outer planets, past Saturn's rings, past Uranus and Neptune, out to the cold dark edges where the sun is just a very bright star among many. But the sun's gravitational influence reaches far beyond even that. There is a region at the very outermost edge of our solar system called the Oort cloud, a vast, diffuse shell of icy bodies that surrounds the sun at an almost unthinkable distance. It begins somewhere around 2,000 times the distance from the Earth to the sun and extends perhaps 100,000 times that distance outward. The long-period comets that occasionally drift into our inner solar system, the ones that take thousands of years to complete a single orbit, are believed to originate here, shaken loose from this distant frozen reservoir by the gentle gravitational nudges of passing stars. The Oort cloud has never been directly observed. It is theorized, modeled, inferred from the paths of comets that carry its fingerprints with them as they travel inward toward the light. It is, in a sense, the solar system's quiet secret, immense and invisible, surrounding us on all sides, known only by what it sends our way. Closer in, but still unfathomably far by human standards, lies a world that has captured imaginations for centuries. Saturn, the sixth planet from the Sun, is perhaps the most visually stunning object in our solar system. Its rings, which appear almost impossibly delicate from afar, are made mostly of ice and rock, ranging in size from tiny grains to chunks as large as a house. The rings stretch out nearly 300,000 kilometers from the planet's surface, wider than the distance from the Earth to the Moon, and yet, in most places, they are less than a kilometer thick. Thin as a piece of paper on a cosmic scale, stretched out flat beneath a golden, glowing world. And here is something that never fails to fill the mind with a quiet kind of wonder. Saturn is the only planet in our solar system that is less dense than water. If you could find a bathtub large enough, an absurd planet-sized bathtub, Saturn would float. Let that image rest in your mind for a moment. A planet, floating. Not far from Saturn, in cosmic terms, lies a world of a very different character. Neptune, the eighth and farthest recognized planet from the Sun, is home to some of the most violent winds in the entire solar system. Storms that move at speeds of over 2,000 kilometers per hour, faster than the speed of sound on Earth, raking across a surface of deep, churning blue. And yet, from here, Neptune appears as nothing more than a small, still blue-green point of light, peaceful as a distant lamp on a winter evening. It is a reminder that distance softens everything, that even the most turbulent things seen from far enough away look serene. There is something comforting in that, perhaps, the idea that perspective, enough of it, can make even a storm look like stillness. Let's talk for a moment about our moon, that faithful silver companion that has hung in our sky for as long as our species has been around to look up and wonder at it. The moon is slowly moving away from us. Every single year, it drifts about 3.8 centimeters further from the Earth, roughly the same rate at which your fingernails grow. It has been doing this since it formed, and it will continue to do so for billions of years to come. In the very distant past, the moon was much, much closer, and it would have appeared enormous in the sky, a great pale disk, looming over a young and restless Earth. And the tides it raised back then would have been extraordinary, vast, powerful surges of ocean, driven by a moon that was practically a neighbor by comparison. Now it drifts away, slowly, unhurriedly. A little further each year. Still beautiful. Still faithful. Just gradually finding its own space. And it turns out that the moon has a far more active history than it may appear. Beneath its quiet, cratered surface lies evidence of ancient volcanic activity. Vast plains of solidified lava called Maria, which is the Latin word for seas. Early astronomers, looking up at the dark patches on the moon's face, imagined they might be great bodies of water, like Earth's own oceans. They weren't, of course, they are ancient lava flows cooled and frozen in place billions of years ago. But the name Maria stuck, and so the moon still carries on its face the memory of a time when astronomers looked up and dreamed of oceans in the sky. It is late now, wherever you are. The world outside is quiet, or nearly so. And somewhere above you, above the ceiling, above the roof, above the clouds and the atmosphere and the thinning edge of sky, the moon is making its patient way across the darkness. And beyond it, Saturn floats serenely on the surface of an imaginary sea. And beyond that, Neptune storms in silence. And beyond all of it, the Oort cloud drifts, vast and invisible, keeping its long and frozen watch. You are here, small and warm and still, at the center of all of it. Rest now. Let these distances settle around you like blankets. We have 82 more facts ahead of us. There is a particular kind of peace that comes with truly letting go of scale. With stopping, just for a moment, the instinct to measure and compare and make sense of size, and simply allowing yourself to exist within it instead. To float in it. To let the distances wash over you like the sound of rain on a window, felt more than understood. That is how we travel through space best, I think. Not by grasping at the numbers, but by letting them carry you. So let them carry you now. We left our solar system quietly at the end of the last chapter. Past the Oort cloud, past the last whisper of the sun's gravity, out into what astronomers call interstellar space. The space between the stars. It was only in 2012 that a human-made object first crossed this threshold. Voyager 1, launched from Earth in 1977, finally slipped beyond the boundaries of our solar system after 35 years of travel. It is the most distant human-made object in existence. Right now, as you lie here in the dark, Voyager 1 is still out there, still moving, still sending signals home, still faithfully reporting back from the void. Those signals, traveling at the speed of light, now take more than 22 hours to reach us. 22 hours. At the speed of light. And it has barely left the neighborhood. The nearest star to our own sun is Proxima Centauri, part of the Alpha Centauri star system, sitting approximately 4.24 light-years away. A light-year, the distance light travels in an entire year, is about 9.46 trillion kilometers. And Proxima Centauri is 4 of those away. Voyager 1, traveling at its current speed, would take approximately 73,000 years to reach it. If it were headed that direction, which it isn't, the stars are not close. They never were. But somehow, knowing that makes them more beautiful, not less. Each one a distant lantern, burning patiently across an almost incomprehensible gulf of darkness, generous enough to be visible anyway. Proxima Centauri is a red dwarf star, smaller, cooler, and far dimmer than our sun. Red dwarfs are actually the most common type of star in the Milky Way, making up somewhere around 70% of all the stars in our galaxy. And yet they are all invisible to the naked eye. Every single star you have ever looked up at and admired on a clear night, every point of light in the sky as seen without a telescope, is either a star larger than our sun, or it is one of our solar system's own planets. The most common stars in the galaxy are completely hidden from our unaided sight. The sky that our ancestors navigated by, wrote poetry about, used to mark their seasons and tell their stories, that sky shows us only the giants. The quiet, common, red glowing majority goes entirely unseen. There is something very human about that, perhaps. We have always been drawn to the brightest things. But brightness, in space, is not always what it seems. Some of the most luminous objects in the night sky are not individual stars at all. They are entire galaxies. The Andromeda Galaxy, for example, is faintly visible to the naked eye on a clear, dark night, appearing as a soft, smudged blur near the constellation of Andromeda. What you are seeing when you look at it is not a star, not a nebula, but an entire galaxy, containing roughly 1 trillion stars, located approximately 2.537 million light-years away. 2.5 million light-years. And it is the closest large galaxy to our own. The light reaching your eyes from Andromeda tonight left that galaxy long before our earliest human ancestors walked the Earth. It has been traveling toward you through the darkness for 2.5 million years, and it arrives tonight, faint and quiet, to rest on the surface of your eye. And here is something even more extraordinary. Andromeda and the Milky Way are moving toward each other. Not drifting idly, but genuinely, gravitationally, inevitably approaching. In approximately 4.5 billion years, the two galaxies will begin to collide. Not crashing together violently the way two rocks might, but interpenetrating, their billions of stars passing through each other like two swarms of fireflies moving through the same summer night, each too far from the others to collide directly, but together pulling and stretching the shapes of both galaxies slowly, beautifully, over hundreds of millions of years, until eventually they settle into something new. a single larger galaxy, still and merged and glowing. Astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda. It exists, for now, only in our calculations. But it is coming, in the slowest, most graceful way imaginable. Rest your mind on that for a moment. 2 galaxies, each containing hundreds of billions of stars, drifting toward each other across millions of light years, drawn together by nothing more than gravity, that most patient of forces, that gentlest of hands. There is no urgency to it, no collision in any human sense of the word, just a slow, inevitable coming together, playing out over timescales that make our entire civilization look like the blink of an eye. The night is deepening now. Your breathing is slower. The world is further away than it was. Let Andromeda drift toward us in the dark. Let Voyager travel its long, faithful road through interstellar space. Let Proxima Centauri burn its small, red, invisible fire 4.24 light-years away. You don't have to do anything with any of it. You only have to rest here in the middle of it all and let it be enormous around you. We have 73 more facts to carry you through the night. There are places in the universe where the ordinary rules begin to bend, where matter behaves in ways that seem, by any reasonable standard, impossible, where gravity becomes so extreme, so concentrated, so absolute, that even our best language struggles to describe what happens there, where the cosmos, in its quiet way, reminds us that for all we have learned, for all our instruments and equations and patient observation, there are still things out here that genuinely defy easy understanding. These places are not frightening, exactly. They are simply profound, deeply, almost incomprehensibly profound. Let's visit them together. When a star much more massive than our Sun reaches the end of its life, it does not go quietly. For millions or billions of years, a star spends its existence in a state of beautiful tension. The outward pressure of nuclear fusion pushing against the inward pull of its own gravity, perfectly balanced, holding the star in its familiar, steady shape. But eventually the fuel runs out. The fusion slows, and gravity, which has been waiting patiently all along, wins. The core of the star collapses in a fraction of a second, faster than thought, faster than any human process. And then the outer layers of the star come crashing inward and bounce back outward in a catastrophic explosion called a supernova. For a brief period, a single dying star can outshine an entire galaxy. One star, in its final moment, burning brighter than 100 billion others combined. It is perhaps the most dramatic event the universe produces. And it happens, somewhere in the observable universe, approximately once every second. What is left behind after a supernova depends on how massive the original star was. For some stars, what remains is a neutron star, one of the most extraordinary objects in all of known physics. A neutron star is the collapsed core of a dead star, compressed so tightly that a single teaspoon of neutron star material would weigh approximately 4 billion tons here on Earth. The entire mass of something larger than our Sun, crushed into a sphere roughly the size of a city, perhaps 20 kilometers across. Neutron stars also spin. Some of them spin extraordinarily fast, hundreds of times per second. And as they do, they beam radiation outward like a lighthouse in the dark. When these beams sweep past the Earth with each rotation, we detect them as rapid, precise pulses of radio waves. These are called pulsars, and when they were first discovered in 1967, the signal was so regular, so mechanical, so unlike anything natural that had been observed before, that the astronomers who found it briefly, and rather wonderfully, nicknamed the signal LGM-1. LGM stood for Little Green Men. It was of course a pulsar. But for a short and delightful moment, the universe had seemed to be saying hello. And then there are the stars that were more massive still. When the most massive stars collapse, not even a neutron star can hold against the force of gravity. The collapse continues past neutrons, past any known state of matter, down into something for which we have only one name and very little true understanding. A black hole. At the center of a black hole lies what physicists call a singularity, a point of essentially infinite density, where the known laws of physics simply stop working. Where our equations produce answers that cannot be physical, which is the universe's way of telling us that our equations, at this particular extreme, are no longer sufficient. Surrounding the singularity is the event horizon, the boundary of no return. Not a physical surface, not a wall or a membrane you could touch, but a threshold, the point beyond which the escape velocity required to leave exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever come back. Not matter. Not energy, not information, not even light itself, which is why they are black. But here is something that may surprise you. Black holes are not, in spite of their reputation, cosmic vacuum cleaners. They do not roam the universe sucking up everything around them. If our Sun were somehow, magically, to be replaced by a black hole of exactly the same mass, which would be a very small black hole. As these things go, the planets of our solar system would continue orbiting exactly as they do now. The Earth would not be pulled in. The gravity at any given distance from a black hole of a certain mass is identical to the gravity at that same distance from any other object of the same mass. What makes black holes dangerous to approach is simply how much mass is concentrated into how small a space. You can get so much closer before the gravity becomes overwhelming. Close enough that the tidal forces, the difference in gravitational pull between the near side of your body and the far side, would stretch you, in the rather evocative terminology of physicists, into something resembling a long, thin strand of matter. They call this process spaghettification. And somehow that word, so cheerful, so domestic, so utterly ordinary, sitting alongside the most extreme physics the universe can produce, feels exactly right. At the center of our own Milky Way galaxy, approximately 26,000 light-years from Earth, sits a supermassive black hole. It is called Sagittarius A, and it contains the mass of approximately 4 million suns. It sits there at the heart of our galaxy, quiet and dark and immense, and every one of those 100 to 400 billion stars, every nebula, every planetary system, every drifting cloud of gas and dust, orbits slowly around it. In April 2019, astronomers released the first ever image of a black hole's shadow. Not Sagittarius A*, but a supermassive black hole at the center of a galaxy called M87, 55 million light-years away. The image, a glowing orange ring of superheated gas surrounding a dark center, was assembled from data collected by 8 radio telescopes positioned across the entire planet, all working together as a single Earth-sized instrument. Humanity had looked at black holes in equations for over a century. And then, one April morning, we finally saw one. There are things in this universe that are humbling not because they diminish us, but because they reveal how extraordinary it is that we are here at all. Small enough to fit in a bed, in a room, in a house, on a planet, beneath a sky full of dying stars and spinning remnants and dark, impossible hearts of collapsed gravity. And somehow able to know all of this. Somehow able to reach out, with our mathematics and our telescopes and our patient watching, and understand, even a little, what is out there. You are a conscious creature in a universe full of wonders that took billions of years to arrange themselves into something capable of wonder. That is not nothing. That is, in fact, everything. Rest now. Let the black holes hold their quiet centers. We have traveled far tonight. Past the moon and the planets, past the edge of our solar system, out through the interstellar dark to the nearest stars, across millions of light-years to Andromeda, down into the impossible hearts of collapsed stellar giants. And now, gently, we are going to come back. Not all the way back. Not yet. But inward in a different sense. Not toward Earth, exactly, but toward you. Because there is a story about space that is not told from a distance. One that doesn't require a telescope or a spacecraft or even a clear night sky to witness. It is a story you carry with you. Inside you, right now, as you lie here breathing slowly in the dark. Every atom in your body was made in a star. Not metaphorically. Not approximately. Literally, physically, chemically, the atoms that make up your bones and your blood and the soft tissue of your brain, the calcium in your teeth, and the iron that carries oxygen through your veins and the carbon that forms the long, elegant chains of every molecule in every cell of your body. All of it was forged in the nuclear furnaces of stars that lived and died long before our sun was born. The hydrogen in your body, the most abundant element in the universe, and the most abundant element in you, is even older than that. The hydrogen you are made of was created in the first few minutes after the Big Bang, 13.8 billion years ago. It has been hydrogen ever since. It drifted through the early universe, gathered into clouds, collapsed into the first stars, was expelled back into space when those stars died, gathered again, collapsed again, drifted through the galaxy for billions of years, fell into the nebula that became our solar system, became part of our Earth, became part of the ocean, became part of a living cell, became part of a long, unbroken chain of life, and eventually somehow became part of you. The heavier elements, the carbon, the nitrogen, the oxygen, were forged in the cores of massive stars, built up slowly over millions of years as the star fused lighter elements into heavier ones, layer by layer like the rings of a tree. When those stars exploded as supernovae, they scattered these elements across the galaxy, seeding the clouds of gas and dust from which new stars and planets would one day form. The heaviest elements of all, gold, platinum, uranium, required something even more violent than a supernova to create them. They are formed in the collision of two neutron stars, an event called a kilonova, where the energies and pressures involved are so extreme that even the universe's most stubborn atomic nuclei can be forced together. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that powers nuclear reactors. All of it was born in the collision of dead stars, billions of years ago, scattered across space, gathered into planets, and eventually, in one small corner of one quiet galaxy, dug out of the ground by a species that had no idea for most of its history where any of it had come from. You breathe in. You breathe out. The oxygen entering your lungs right now was produced by ancient stars and by billions of years of photosynthesis, by plants and algae on this planet. The nitrogen in the air around you drifts up from the earth and down from the sky in a cycle that has been running since long before the first human breath. The carbon dioxide you exhale will be taken up by a leaf tomorrow, turned into sugar by sunlight, and will eventually, in one form or another, become part of something else entirely. You are not separate from this cycle. You are an expression of it. There is a particular kind of nebula called a planetary nebula, a name that is charmingly entirely misleading, since planetary nebulae have nothing whatsoever to do with planets. They were named by early astronomers who, peering through small telescopes, thought these soft, glowing, circular clouds looked a little like the disk of a planet. They are, in fact, the expelled outer layers of dying stars, the beautiful, colorful shells of gas and dust that a sun-like star throws off as it reaches the end of its life, lit from within by the hot remnant core left behind. They are, in other words, a star in the act of giving itself away. The Helix Nebula, the Ring Nebula, the Cat's Eye Nebula, each one a slowly expanding cloud of material that was, not so long ago in cosmic terms, the outer layers of a living star. Each one drifting outward through space, cooling, dispersing, seeding the interstellar medium with the elements forged over a stellar lifetime. Each one, in its way, an act of extraordinary generosity. Our own sun will do this one day. In about 5 billion years, as its hydrogen fuel runs low, it will swell into a red giant, expanding outward to perhaps 100 times its current size, engulfing Mercury and Venus, scorching the Earth. And then eventually it will shed its outer layers in its own planetary nebula, dispersing itself across the local galaxy, leaving behind only its small, dense core glowing faintly as a white dwarf, slowly cooling over billions of years into something dark and cold and still. The material it scatters will drift, will cool, will gather, will, in some far future time and place and circumstance impossible for us to imagine, perhaps become part of something new. Another planet, another ocean, another long chain of molecules finding its way, improbably, toward something that breathes and wonders and looks up. You are made of things that have already done all of this once before. Atoms that have been stars and gas clouds and oceans and rock, and creatures living and dying across billions of years of an unbroken, unimaginable story, and which find themselves, right now, arranged in the particular and extraordinary pattern that is you. Lying here, breathing slowly, letting the universe wash over you. The astronomer Carl Sagan said it most simply, and most beautifully: we are a way for the cosmos to know itself. Not observers standing outside the universe, looking in, but part of it, woven into it, made of it, through and through all the way down. You are not looking at the universe tonight. You are the universe looking, then recedes to. And now perhaps it is time to let your eyes stay closed. Let the stars do their slow and ancient work up above. Let the nebulae drift and glow. Let the atoms in your bones remember, in whatever way atoms remember, the long journey that brought them here. You don't need to hold any of it. It will all still be there when you wake. We have 55 more facts still to share with you. There is something deeply comforting about mysteries. Not the urgent kind. Not the kind that demand solving, that keep you awake with their loose ends and unanswered questions. But the other kind. The quiet kind. The kind that simply sit with you in the dark, vast and patient and content to remain unknown, asking nothing of you except that you acknowledge them. Space is full of that kind of mystery. And tonight we are going to rest inside the greatest one of all. If you were to add up everything we have talked about so far tonight, every star in every galaxy, every planet, every moon, every comet and asteroid and cloud of interstellar gas and drifting grain of cosmic dust, every single thing in the universe that we can see, detect, measure, or interact with in any way, all of it, together, accounts for approximately 5% of the total content of the universe. 5%. The remaining 95% is made of things we cannot see, cannot touch, cannot detect directly, and do not, if we are being honest, truly understand. About 27% of the universe is made of something called dark matter, and roughly 68% is made of something even stranger, called dark energy. The universe, in other words, is almost entirely made of things that are, to us, invisible. What we have mapped and measured and marveled at, all the stars and galaxies and nebulae and black holes and everything else, is little more than a thin, luminous frosting on a cake whose main ingredients remain almost entirely unknown. Dark matter is not dark in the way that a room is dark when you turn off the light. It does not absorb light or block it. It simply does not interact with light at all. It neither emits nor reflects nor absorbs electromagnetic radiation of any kind. It passes through ordinary matter, through walls, through planets, through you, right now as you lie here, without any interaction whatsoever, leaving no trace, making no impression, utterly indifferent to everything around it. The only way we know it exists is through gravity. Dark matter has mass, and mass bends space and pulls on other matter, and it is through these gravitational effects that we have been able to map, at least in broad outline, where dark matter tends to gather. And what we have found is that dark matter forms a kind of vast invisible scaffolding throughout the universe, a cosmic web of filaments and nodes and sheets, spreading across unimaginable distances, and it is along this scaffolding that ordinary matter, the 5% we can see, has gathered and clumped and eventually formed galaxies and galaxy clusters, and the large-scale structure of everything we observe. The galaxies we see are, in a sense, lit decorations hanging on an invisible frame. Beautiful, yes, but not the structure. Not the thing that holds it all together. Without dark matter, our galaxy would fly apart. The stars in the outer regions of the Milky Way orbit the galactic center far faster than they should, given the amount of visible matter that can be observed. By rights, by the laws of gravity as we understand them, those outer stars should be moving more slowly, just as the outer planets of our solar system move more slowly than the inner ones. But they don't. They move fast. Too fast. Unless there is additional mass that we cannot see, a vast halo of dark matter surrounding and permeating the galaxy, providing the extra gravitational pull needed to keep everything together. The numbers work. The observations are consistent. And yet no one has ever directly detected a dark matter particle. We have designed extraordinarily sensitive experiments, buried deep underground to shield them from interference, cooled to temperatures near absolute zero, running for years at a time, and so far, silence. Dark matter remains a presence felt only by its effects. Like wind, known by the movement of leaves. And then there is dark energy, which is stranger still. In 1998, 2 independent teams of astronomers were studying distant supernovae, using them as cosmic measuring sticks to chart the expansion of the universe. The universe has been expanding since the Big Bang, and the expectation was that this expansion should be slowing down over time, gradually braked by the mutual gravitational attraction of all the matter within it. What they found instead stopped the scientific community in its tracks. The expansion of the universe is not slowing down. It is speeding up. The galaxies are not just moving apart, they are accelerating away from each other, driven by some form of energy embedded in the fabric of space itself, an outward pressure that grows stronger as space expands, pushing everything apart faster and faster with every passing billion years. This discovery earned its researchers the Nobel Prize in Physics in 2011. And the force responsible, whatever it is, was named dark energy. Not because anyone understood it, but because it needed a name, and because it was like dark matter, entirely invisible, and because sometimes the most honest thing science can do is name something clearly and admit that the naming is currently the limit of our understanding. The eventual consequence of dark energy, if it continues to accelerate the universe's expansion indefinitely, is a future so remote it barely qualifies as a timeline at all. Trillions upon trillions of years from now, the expansion of space will have carried all other galaxies so far from ours that they will no longer be visible. The light from them, stretched thinner and thinner by the expanding space through which it travels, will have redshifted into wavelengths too long to detect. Any civilization existing in the Milky Way at that unimaginable future date will look out into the universe and see almost nothing. A handful of gravitationally bound local galaxies, perhaps, and beyond them, darkness. No evidence at all of the vast cosmic web that surrounds us now. They will not know that there are hundreds of billions of other galaxies out there. The universe will have hidden them, carried them over a horizon of distance from which no signal can ever return. We live, it turns out, at a fortunate time. A time when the universe is still young enough, still compact enough, that we can look outward and see the full extraordinary sprawl of what is there. In the deep future, that view will be gone forever. It is a strange and humbling thought. That knowledge itself has an expiry date. That the universe contains information that will one day become permanently, irretrievably inaccessible. Not because we failed to look, but because space itself will have carried it beyond reach. But that is a grief for an unimaginably distant future. Right now, tonight, the galaxies are still there. Hundreds of billions of them, spread across the observable universe, glowing softly through the dark. The cosmic web still shimmers with its invisible threads. Dark matter still holds our galaxy together with its patient, unseen hands. And dark energy still does its slow, mysterious work, breathing the universe gently, steadily outward in every direction at once. It is all so much larger than anything we need to hold on to tonight. We have 46 more facts to carry you through to morning. Are we alone? We don't know the answer yet. And tonight, we are not going to pretend that we do. But we are going to wander through what we do know. And what we know, it turns out, is already extraordinary enough to take the breath away. For most of human history, the question of whether other planets existed beyond our solar system was entirely philosophical. There was no way to look. The stars were too far away, the instruments too limited, the signal too faint. Other worlds, if they existed, were invisible to us, a matter of speculation rather than observation. That changed in 1992, when the first confirmed exoplanets, planets orbiting a star other than our Sun, were detected. And then again, more dramatically, in 1995, when the first exoplanet orbiting a Sun-like star was confirmed. And then the detections began to accumulate. Slowly at first, then faster, then in floods, as our instruments improved and our techniques refined, and the sheer abundance of the universe's planetary generosity began to reveal itself. As of now, astronomers have confirmed the existence of more than 5,500 exoplanets. 5,500 other worlds, each one orbiting its own star, each one unique, each one a place that exists whether or not anyone has ever thought about it. And that number, large as it is, represents only the planets we have managed to detect, in a small region of our own galaxy, using instruments that are still, by any honest measure, relatively crude. The true number of planets in the Milky Way alone is estimated to be in the hundreds of billions. There are, in all likelihood, more planets in our galaxy than there are stars. Many stars host not one planet, but entire systems of them. The universe, it turns out, is extraordinarily, almost recklessly, full of worlds. Among those worlds, astronomers have found some that sit in what is called the habitable zone of their star, the range of orbital distances where liquid water could exist on a planet's surface. Not too hot, not too cold. The distance at which conditions might, under the right circumstances, be friendly to life as we understand it. This zone is sometimes called, with a warmth that scientists rarely permit themselves, the Goldilocks zone. And within it, we have already found planets that are roughly Earth-sized, roughly Earth-like in density, rocky rather than gaseous, orbiting stars not entirely unlike our own. We have found them. They are there. We have not visited them. We cannot see their surfaces. We do not know if they have oceans or atmospheres or anything else. But they exist in the habitable zones of their stars, and their existence alone is enough to make the imagination go very quiet and very still. The nearest of these potentially habitable worlds is orbiting Proxima Centauri, the same red dwarf star we visited earlier tonight, our closest stellar neighbor at 4.24 light-years away. The planet, called Proxima Centauri b, is estimated to be roughly Earth-sized and sits within its star's habitable zone. Whether it is actually habitable is another question entirely. Proxima Centauri is a red dwarf, and red dwarfs are prone to violent stellar flares, sudden, intense bursts of radiation that could strip away a planet's atmosphere over time, rendering the surface inhospitable regardless of its distance from the star. Proxima might be a warm, watered world. It might be a scorched and airless rock. We do not yet have the instruments to know for certain. But it is there. The nearest potentially Earth-like world is orbiting the nearest star. The universe has arranged things with what feels, in this moment, almost like consideration. In the search for life beyond Earth, scientists have developed a framework, a set of conditions considered necessary, or at least highly favorable, for life as we know it. Liquid water, a source of energy, the right chemical ingredients, stability over long timescales. And as we look around our own solar system, we find, to a quietly startling degree, that these conditions exist in more places than we ever anticipated. Europa, one of Jupiter's moons, is covered in a smooth shell of ice. Beneath that ice, warmed by the tidal flexing caused by Jupiter's immense gravity, astronomers believe there is a liquid water ocean. Not a small one, an ocean that may contain twice as much liquid water as all of Earth's oceans combined. Hidden beneath the ice, dark and pressurized and utterly unknown, this ocean has existed for billions of years. Whether anything lives in it, we cannot say. But the conditions for life, liquid water, chemical energy from the seafloor, stability, are present. And on Earth, life has been found in environments that are, by any surface standard, impossibly harsh. Hydrothermal vents on the ocean floor, miles below where sunlight reaches. Acidic hot springs. Antarctic ice. The interior of nuclear reactors. Life, on Earth at least, is stubborn to a degree that has repeatedly surprised us. It finds a way into almost any crack the universe offers. There is another moon worth pausing on. Enceladus, one of Saturn's moons, small and white and brilliant, has been found to be actively venting water vapor and ice particles into space from geysers near its south pole. The Cassini spacecraft, which orbited Saturn for 13 years before its mission ended in 2017, flew directly through these plumes and detected water, salts, silica, and organic molecules, the chemical building blocks associated with life. Enceladus is venting the contents of its subsurface ocean directly into space. It is, in a sense, offering us a sample, telling us, in the only way a moon can, that something interesting might be happening beneath its surface. We have not found life beyond Earth. That is the honest, important truth that must sit alongside all of this wonder. We have found conditions. We have found chemistry. We have found worlds and moons that are not obviously hostile. But the thing itself, the microbe, the signal, the unambiguous signature of biology, remains for now undiscovered. And yet, the universe is 13.8 billion years old. It contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. Most of those stars have planets. Many of those planets sit in habitable zones. The chemistry of life, carbon, hydrogen, nitrogen, oxygen, is among the most common chemistry in the cosmos. If life arose here, on this small, wet, unremarkable planet, orbiting an average star in the quiet suburbs of an ordinary galaxy, the silence feels less like an answer, and more like a question we haven't yet learned how to ask properly. And so we keep listening, keep looking, keep building better telescopes and sending better spacecraft, and designing more sensitive instruments to examine the atmospheres of distant worlds for the chemical fingerprints of biology. We keep asking the question patiently in every direction at once into a universe that has so far not replied, but that is so vast and so old and so extraordinarily full of places where the conditions are right, that the asking itself feels less like searching for something unlikely and more like waiting for something inevitable. You are lying here, small and warm in the dark, on a planet that is, as far as we currently know, the only confirmed address of life in the entire universe. That is either the loneliest thought imaginable, or the most remarkable, perhaps both at once in the way that the most honest things often are. Sleep now. Let Europa's hidden ocean drift through your dreams. Let the geysers of Enceladus vent their quiet plumes into the dark. Let Proxima Centauri be turned slowly in the faint red light of its star, keeping its secrets just a little longer. We have 37 more facts still to share. It is this. When you look at the night sky, you are not seeing the universe as it is. You are seeing the universe as it was. Light travels fast, faster than anything else in existence, but it does not travel instantly. It takes time. And because it takes time, every point of light you have ever looked up at in the night sky is not a window onto the present moment, but a message from the past. A photograph taken at a specific moment in history that has been traveling toward your eyes ever since. The moon on a clear night is the most recent image in the sky. The light reaching your eyes left the lunar surface approximately 1.3 seconds ago. What you see when you look at the moon is where the moon was 1 1/3 seconds in the past. Almost perfectly current by cosmic standards. Almost, but not quite. The sun, as we noted earlier, is 8 minutes and 20 seconds behind. The face of the sun you saw today, if you glanced at it through cloud or at the horizon, showed you a sun that existed before your morning had properly begun. The nearest star beyond our sun, Proxima Centauri, shows us light that left it 4.24 years ago. When that light departed, whatever was happening on Earth 4.24 years ago was the present moment. Elections had not yet happened. Children had not yet been born. Certain people who are alive tonight were, for years ago, in entirely different chapters of their lives. And that is the nearest star. The bright stars of the night sky, the ones with names, the ones our ancestors drew lines between to make their constellations, are mostly somewhere between a few dozen and a few thousand light-years away. Betelgeuse, the red supergiant that marks the shoulder of Orion, is approximately 700 light-years distant. The light arriving from it tonight left that star sometime in the 14th century, around the time of the Black Death, when Europe was in the grip of a plague that would kill a third of its population, when the great cathedrals of the medieval world were still being built, when no human alive had any concept of what a light-year was, or what stars were, or that the reddish point of light in the winter sky was a dying giant hundreds of times larger than our sun. That light has been traveling ever since, through 700 years of human history, through every war and discovery and revolution and quiet ordinary life lived between then and now. And tonight it arrives and falls on your face and you receive it without ceremony because that is how light works. It travels and arrives and is absorbed and asks nothing in return. Betelgeuse is a red supergiant nearing the end of its life. At some point, perhaps in the next 100,000 years, perhaps sooner, perhaps already, it will explode as a supernova. When it does, it will be briefly visible in the daytime sky, potentially bright enough to cast shadows at night, a second point of light in the heavens startling enough to have been noted by every culture on Earth. There is a real possibility, not a certainty, but a genuine possibility, that Betelgeuse has already exploded. That 700 years ago, or 500 years ago, or last Tuesday in Betelgeuse's local time, the star ceased to exist in its current form. And we would not know. We cannot know. The light from that explosion, if it has happened, is still on its way, traveling toward us through the dark at 300,000 kilometers per second, carrying news of a death we have not yet received. We are, in this sense, always reading old letters from the sky. And some of those letters contain news we do not yet know. The deepest images ever taken of the universe make this feeling almost overwhelming. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, carefully chosen patch of sky, a region near the handle of the Big Dipper constellation, so apparently empty that some colleagues argued it was a waste of precious telescope time. They kept the shutter open for 10 consecutive days, collecting every photon of light that passed through that tiny window. What came back was the Hubble Deep Field, an image containing approximately 3,000 galaxies, each one a vast island of hundreds of billions of stars, each one so distant that the light in the image had been traveling for billions of years. Some of the galaxies in that image are seen as they were when the universe was less than 1 billion years old. Infant galaxies, in the early chapters of their existence, caught in a snapshot that took 10 days to take and billions of years to arrive. The patch of sky they observed was, by angular measurement, about 1/13 millionth of the total sky. And in that sliver, 3,000 galaxies. Extrapolated across the entire sky, this suggests the observable universe contains somewhere in the region of 2 trillion galaxies. 2 trillion. Let that number simply exist for a moment. Don't try to picture it. Don't try to populate it with stars and planets, and the long arithmetic of possibility. Just let it sit there, in the comfortable darkness behind your closed eyes, as large and quiet and undemanding as it actually is. 2 trillion galaxies. Each one a universe in miniature. Each one ancient and distant and burning. There is a concept in physics called the light cone, the boundary in space-time that defines what any given point in the universe can possibly see, or be seen by, or influence, or be influenced by. Because light travels at a finite speed, there are regions of the universe so distant that no signal from them could ever reach us, regardless of how long we waited, because the expansion of space between us and them is carrying them away faster than light can cross the gap. We exist within our own light cone, a bubble of possible knowledge, possible connection, possible influence. Everything outside it, and there may be vastly more universe outside our observable bubble than within it, is permanently, irrevocably beyond reach. We will never see it. We will never know what is there. Not because it doesn't exist, but because the universe is under no obligation to be fully knowable by any single point within it. That is not a tragedy. It is, when you sit quietly with it, something closer to a kind of grace. The universe is allowed to be larger than our knowing. The sky is allowed to keep its depth. The darkness between the stars is allowed to hold things that no eye will ever see, no mind will ever reach, no story will ever tell. You are one point of awareness in an unimaginably vast web of space and time, looking outward through a narrow window of possible knowledge, receiving ancient light from a universe that began long before you arrived and will continue long after you are gone. And yet here you are, noticing, wondering, receiving the light, that, of all the facts we have shared tonight, may be the most extraordinary one. Not the distances, not the timescales, not the billions and trillions of galaxies burning in the dark, but the fact that something in all of this, something small and warm and temporary, lying still in a room somewhere on a pale blue planet, is paying attention. Rest deeply now. Let the old light continue its journey toward you and past you and onward into the dark. We are close now, close to the end of our first hour together, close to the place where words begin to blur at the edges and thoughts become something looser and slower and more like dreams than like thinking. This is where we want to be. So for this chapter, we are going to slow down even further. We are going to let go of the vast and the overwhelming and the numerically staggering, and instead we are going to linger on some of the smaller, quieter, more intimate details of space. The things that don't make headlines. The things that make you smile softly in the dark and then forget what you were thinking about, and then find that you are already somewhere else entirely. Let's begin with something you may never have considered before. Space is silent. Not metaphorically silent, the way a library is silent or a winter morning is silent. Literally, physically, completely silent. Sound is a wave that travels through matter, through air, through water, through solid objects. And in the near vacuum of interstellar space, there is not enough matter for sound to propagate through. You could stand, if such a thing were possible, in the space between the stars with a supernova exploding nearby, and you would hear absolutely nothing. The most catastrophic event the universe produces would pass you in complete and perfect silence. The explosions you have seen in films set in space, the roaring engines, the crashing debris, the enormous booming detonations, are all inventions. Generous ones, perhaps, but inventions nonetheless. The universe, in reality, conducts all of its most dramatic business in total silence. And yet space is not entirely without waves. Sound requires matter to travel through, but there is a medium in space that is dense enough, in certain places, for something like sound to propagate. The Perseus Galaxy Cluster, a vast collection of galaxies bound together by gravity, surrounded by a cloud of hot gas, was found by NASA's Chandra X-ray Observatory to contain actual pressure waves moving through that gas. Waves caused by the enormous black hole at the cluster's center, periodically releasing jets of energy that send ripples outward through the surrounding medium. These pressure waves, which are, in the most technical sense, sound waves, have a frequency so extraordinarily low that they sit 57 octaves below middle C on a musical scale. So low that a human ear could not detect them even if they were somehow transmitted through air. so low that a single cycle of the wave takes approximately 10 million years to complete. In 2022, NASA converted these pressure waves into something audible by scaling the frequency upward into the range of human hearing. And when they did, the Perseus cluster sounded, hauntingly unexpectedly, almost unbearably beautifully, like something alive. The stars themselves have colors, if you look carefully enough. On a clear, dark night, away from the light of cities, the brightest stars reveal their tints to a patient eye. Blue-white stars like Rigel or Sirius, burning at tens of thousands of degrees, shimmer with a cool blue intensity. Yellow stars like our own sun glow warm and steady. Orange giants like Arcturus carry a faint amber warmth. And red supergiants like Betelgeuse, that ancient shoulder of Orion we visited earlier tonight, glow with a deep, ruddy autumnal color, the color of embers of cooling things of great age. A star's color is a direct measure of its surface temperature. Blue means hot, extraordinarily, ferociously hot. Red means cooler, still tens of thousands of degrees by any earthly standard, but cool for a star, the way the edge of a flame is cooler than its center. The color of a star is its temperature made visible, broadcast across light years for anyone patient enough to notice. The night sky, looked at this way, is not black and white. It is painted in subtle, extraordinary color. It has always been painted this way. We simply have to slow down enough to see it. Here is a fact that has a particular quality of quiet wonder to it. On a clear night, the human eye can see approximately 2,000 to 2,500 stars from any given location. That sounds like a great many, standing in a dark field with your head tilted back and the whole arch of the sky spread above you. But it is, by the numbers, almost nothing. Those 2,500 stars represent a fraction so small it barely registers. Roughly 0.0000001% of the stars in the Milky Way alone. The sky as we see it, the sky that has been the entire ceiling of human experience for as long as our species has existed, the sky that every poet and shepherd and sailor and philosopher has ever looked up at, shows us a number of stars so small, relative to what is actually there, that it is barely a suggestion. A rumor of the actual galaxy. The faintest imaginable sketch of the real thing. And it is still the most beautiful thing most people have ever seen. There is water in space. Not just theoretically, not just in ice on distant moons, but freely distributed throughout the galaxy in clouds of gas and dust between the stars. In 2011, astronomers discovered a reservoir of water vapor surrounding a quasar, a brilliantly luminous active galactic nucleus, located about 12 billion light-years from Earth. The reservoir contained approximately 140 trillion times the volume of water in all of Earth's oceans combined. 140 trillion times. Water, that most essential, most intimate, most taken for granted of molecules, is not a rare or special feature of Earth. It is a common product of stellar chemistry, found throughout the cosmos in quantities that make our oceans look like a single drop on the surface of something incomprehensibly vast. The universe is full of water, and somewhere perhaps some of it is full of life. Let your breathing slow now. Let each breath come a little easier than the last. We are almost at the edge of sleep, and there is one more thing to mention before we let this segment rest. It concerns the International Space Station, that small, brilliant, human-built outpost that has been continuously occupied since November of the year 2000. Right now, or close enough to right now that the difference doesn't matter, there are human beings aboard it. Astronauts from different countries, different backgrounds, different languages, living and working together in a pressurized metal cylinder roughly the size of a 6-bedroom house, orbiting the Earth at approximately 28,000 kilometers per hour. At that speed, they circle the entire planet once every 90 minutes. 16 sunrises in a single day. 16 times the sky darkens and then blazes and then darkens again, the Terminator line, the boundary between day and night, sweeping across the curve of the Earth below them in a slow and endless rhythm. On a clear night, the ISS is visible to the naked eye from the ground. A steady, bright, non-blinking point of light moving purposefully across the sky from west to east, there and then gone in a few minutes. If you have ever seen it, you have seen human beings. We have come a long way tonight. Further, perhaps, than any distance you could measure in kilometers or light years, or the lifetimes of stars. We have traveled through the solar system and out beyond it, through the Milky Way and across the Gulf to Andromeda, down into the hearts of black holes and up through the expanding fabric of spacetime itself, through the invisible architecture of dark matter and the quiet acceleration of dark energy, across the surfaces of alien moons and into the atmospheres of distant worlds, back through time on beams of ancient light, and all the way home again to a small metal station circling our small blue planet at 28,000 kilometers per hour. And now we are here, at the end, which is also, in the way of all good endings, a kind of beginning. There is a photograph. It was taken on February 14, 1990, by the Voyager 1 spacecraft. The same Voyager 1 we met earlier in our journey, the one that has since crossed into interstellar space and continues even now its long, faithful travel through the dark. At the request of the astronomer Carl Sagan, mission controllers turned Voyager's camera back toward the inner solar system one final time before the spacecraft's imaging systems were shut down to conserve power for the long journey ahead. From a distance of approximately 6 billion kilometers, just beyond the orbit of Neptune, Voyager turned and looked back. And there, in the resulting image, suspended in a beam of scattered sunlight, was Earth. A point of light less than a pixel across. A pale, pale blue dot, almost lost in the vastness of the image surrounding it. Our entire world. Every mountain and ocean and city and war and love story and moment of grief and moment of joy that had ever occurred in all of human history. Visible as a mote of dust suspended in a sunbeam. Carl Sagan wrote about that image with a tenderness that has never quite been matched. He spoke of how every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher and student, every saint and sinner in the history of our species, lived out their lives on that pale blue dot. Every moment of human certainty and human doubt, every empire that ever rose and fell, every act of cruelty, and every act of extraordinary kindness, all of it, on that tiny, fragile, almost invisible point of light. Our planet is small. We have always known this in some abstract way, but the photograph made it undeniable. Made it visible. Made it something you could hold in your mind not as a number or a ratio, but as an image, a real, specific, photographed image of our actual home, from far enough away to see it whole. And what it looks like from out there is precious. Not powerful. Not permanent. Not inevitable. Precious. The Earth itself is approximately 4.5 billion years old, roughly the same age as our Sun, both having formed from the same collapsing cloud of gas and dust. In that time, our planet has been through extraordinary transformations. It has been struck by objects large enough to reshape its surface entirely. It has frozen, nearly pole to pole, in episodes called Snowball Earth, when the entire planet was encased in ice kilometers thick. It has been so warm that forests grew near the poles, and the oceans were bathed in temperatures that would seem tropical to us now. It has been struck by the asteroid that ended the reign of the dinosaurs. A rock approximately 10 to 15 kilometers across that hit the Yucatan Peninsula 66 million years ago with the force of billions of nuclear weapons, darkening the sky and collapsing the food chain in a matter of years. And through all of it, through every catastrophe and transformation, and ice age and mass extinction, life persisted. Changed, adapted, lost whole branches of its family tree and grew new ones, retreated and returned and evolved and diversified and eventually, improbably became curious. Became something that wondered where it came from. Became something that looked up. The history of astronomy is, in one sense, the history of perspective. Each time we have found a way to see further or more clearly, or from a new angle, we have discovered that the universe is larger, older, stranger, and more generous than we had previously imagined. Every expansion of our view has come with a corresponding expansion of our sense of what is possible. Copernicus showed us that the Earth is not the center of the solar system. Galileo pointed a telescope at the sky and found moons circling Jupiter, proving that not everything orbits us. Hubble showed us that the faint smudges of light visible through telescopes were not nearby gas clouds but entire galaxies, each containing hundreds of billions of stars, each inconceivably remote. The Hubble Space Telescope showed us 2 trillion of them in a patch of sky we thought was empty. Voyager showed us what we look like from outside. Each revelation, in its time, felt like a demotion, a shrinking of our importance, a reduction of humanity's place in the scheme of things. But there is another way to read the same story entirely. Every time the universe turned out to be larger than we thought, our ability to understand it grew to match. Every time the cosmos revealed a new depth, a new scale, a new strangeness, we were there, with our mathematics and our telescopes and our restless, extraordinary minds, to receive it, to measure it, to give it names and write down its properties and fit it into a picture that, slowly, imperfectly, with tremendous effort and tremendous beauty, makes sense. We are small, but we are not passive. We are temporary, but we are not insignificant. We are made of the same atoms as everything else in the universe, but we are the part that knows it. And now here is our final fact. Our 100th wonder. Or rather, it is not quite a fact. It is something between a fact and a feeling, which is perhaps the most honest place for any great journey to end. In the entire observable universe, across all 2 trillion galaxies, across all the hundreds of billions of stars in each of them, across all the planets and moons and asteroids and comets and clouds of gas and dark rivers of dust. In all of that, we have, so far, found exactly one place where something looks up at the night sky and wonders what it is looking at. Here, this planet, this pale blue dot. Whether that makes us lonely or luminous, whether it fills you with a feeling of cosmic solitude or cosmic responsibility or simply a quiet, unnameable awe, that is yours to decide. Perhaps it changes from night to night. Perhaps it changes depending on how tired you are, or how loved you feel, or how long it has been since you stood somewhere dark and let the full weight of the sky fall on you. But tonight, it is enough to know that you are here. That you have spent this hour with the universe, listening to it, letting it wash through you. That you know a little more about the darkness above you than you did when you closed your eyes. The stars are still there, above the ceiling and the roof and the clouds. Saturn floats on its invisible sea. Europa's ocean turns in the dark,